they go for the allotted extended time?
Yes. Okay, so let's start with the field trip on Friday. I know one person who needs a ride. Does anyone else need a ride? Okay, going with that, so no one else needs a ride. The Nebraska Academy of Sciences annual meeting is this Friday and occurs at Nebraska. I hope you guys can see when I click stuff and it doesn't take it. Nebraska Wesleyan University, which is 5000 St. Paul Avenue. To get there, just get on 48 and travel north. Travel north on 48, and eventually you'll see a sign that says Nebraska Wesleyan University that way. And that's like 2 blocks away from 48th Street. So it's pretty easy to get there. And of course, I recommend all of us, just use our GPS to make sure we get there. There is a map of Nebraska Wesleyan University here. And check-in, the place you need to go to check in is, I believe it's here. It's always been here in the past. And so I think it's still going to be there. Where I circled there. Olin Hall is 2, and then 3 is Olin Lecture Halls in the planetarium.
So the entrance to that, is that going to be...
Sorry, I can't search the web on Apple Watch.
Yeah.
From the north side of the map from here, or is it going to be like from the...
Okay, so we'll be coming in. If you're coming in from Lincoln, this is 48th Street here. And it used to be that I parked where the new science building is. Here's the new science building where almost all the sessions will be. All the ones that are required are going to be in there. I've never been in there. That's where I parked last year. So you have a parking pass. The last page is a parking pass. Notice this parking pass is good everywhere except for no parking in blue tag areas, handicap stalls, reserved stalls, or designated no parking zones, obviously. So this is a pretty broad parking permit because you'll need to find a place to park. So you'll be coming in here, and I actually usually turn here on there. But because they've changed things around, I'm not exactly sure what the best way to get there is. I have oftentimes found myself parking over here next to the frat houses. So check-in is there either in Building 2 or Building 3. It's in Olin Hall. And there should be signs telling us where to check in. Check-in starts at 7:30, and the first sessions start at 8. Now, I'll talk about timing there in a minute. You're required to fill out talk summaries for 4 talks. Talks are generally around 10 to 15 minutes in duration. So you need to be there for a minimum of an hour to get your number of talks in. And 2 of those 4 talks need to be from sessions included here. Notice there are sessions afternoon and sessions in the morning, so you can come anytime and get those in.
I know the teaching ones.
I put those in for you too. So then you have 2 poster summaries. And this is where morning is far preferred. The poster sessions, I changed that myself. Okay, we're not going to highlight then. The poster sessions are at 9:10 and 10:30 in the morning. And you really need to be there at 9:10 or 10:30. 9:10 is the better one. My experience is the people with the posters are often there for the 9:10 to about 9:30. So you only have like 20 minutes there. And they often don't come for the second one at 10:30. So if you can be there for the 9:10 one, that's going to be your best time to get your posters in. I want you to observe the posters, interact with the people who are there. The way we do this in science is you have a poster and you have somebody there with the poster. You come up, you read the poster, you ask them questions. Don't just come up and ask them a question without reading it. You're not going to ask an intelligent question probably if you do that. They come up and read it. They might, depending on the person, they might offer to give you some assistance or a summary or whatnot. But pay attention to those posters because you have your own posters that you have to turn in next Tuesday. And so we don't want to, well, we want you to be able to use this to see what works and what doesn't work. And you will see different variations. One of the big things that we all do wrong with posters is we try to put too much in there. And so it gets to be really tiny. You have to do all like this to try to read it. That's not an effective poster. You need to have it so you can read it at a distance and have some white space. So, observe what you like and what you don't like and use that to help guide you with your posters. Yeah.
So what you want us to turn in is pretty much the 4 talks and something about, do you want us to turn in something for poster or?
Okay, so what I want you to turn in is what's in this plus your badge. Notice that we have here this form along with your badge must be turned in by class time on Monday, April 15. And will count as a homework assignment.
That's a link.
No, it's not a link actually.
Oh.
So you need to turn in this with it filled out. So make sure you get your name badge, check in. You're supposed to wear it there. I don't know that anyone's ever going to kick you out of a meeting, but it's your sign that you've paid your entry fee, or we've paid it for you, obviously. I will get to what you're actually doing is I just want to go a little straightforward through this. Yes, DJ?
Can you have a clipboard for this?
Yeah.
That'll help a lot. 'Cause I'm just walking around writing, because otherwise it'll just be kind of floppy.
I don't have them for you, but you can have a clipboard. Make sure we're clear on. I thought you said, can you have a clipboard? And I thought maybe Okay, so what to do there? First, you will find people in all ranges of clothing. Some will be dressed really well, like, they're giving a business presentation or going to church. And some will be dressed really slacker. We want our students and our teachers to give a good impression. So we would like you to dress, business casual, which is, today is one of my less dressed up days, especially because I'm wearing my holy pants. But like I try to dress for teaching. Don't come wearing your sloppiest clothes. Try not to walk in or out when somebody's talking. You don't want to be rude. You don't want to be disruptive. You will find people who do walk in and out during talks, but just don't be one of them. You will also find a lot of people standing outside the room waiting for the talk to end and then all rushing in at once. That's the standard thing to do. Please don't have your cell phones. We don't want to hear cell phones. We don't want to see people there on their cell phones during the presentations. We want people to be getting something out of them. Don't distract with talk. Don't be sitting there, like me sitting next to Nathan. Hey, did you see that? That's funny. Don't do that. Save questions until the end of the presentation. Some people will say, feel free to ask me questions anytime when you're confused or have a question. But even when they say that, it's best to wait until they're done with the presentation because they only have X amount of time to finish the presentation, and then they have another few minutes after that to answer questions. And so if they're getting interrupted during the presentation, they may not get to finish, and we want them to be able to finish. So those are some basic protocols, just how to attend the conference and to represent us well. There is a link here so you can see the entire program. So you can see all of the different talks. You have to go to, like I said, 2 talks that are from the categories that I listed and poster sessions. But you could go to any other 2 talks you want. And the conference goes all day long. And you might find, wow, this talk on biochemistry is so intriguing to me. I got to go to that talk. Great. You can include that as one of your 2 that you report on. And of course, you can go to a lot more talks than the 4 you report on. So how do you do your reporting? Here's how you do your reporting. So first of my talks that I'm attending, the location and time, or the session name and the location. So let's say that I'm just going to take information from here. I'm going to go to chemistry and physics, the physics section in Ackley 320. So I put here change it to a pin. Chem and physics. Ackley, was it 320? you'll be able to get it more accurate than me who can't remember. Okay, here. Now I don't have to switch back and forth. Yes, it was exactly 3:20. So you put that down there just so I know which session it is so I can go check and correlate. Title of the talk. So I don't have listed here, so I'm just going to make something up. Okay, I just made up a title. Measuring the speed of light and wide bandgap dielectrics. Just make it up. Presenter, you are smart. All right. The actual time it started. There are start times listed in the program for each of the talks. So you can go beforehand and plan, this is the one I want, but they often don't start at the actual listed time. So here you'd put the actual time. So it started at 8:23 a.m. Then put your notes that you take during the talk. So actually pay attention and have some notes. Right? I don't want to see, well, I just didn't take notes on this one. I want to see the notes you took on it. So take notes on it. And then put down here, you don't have to raise your hand and ask a question. If you do, that's great. But put down here a question that was just bugging you. Why did you only study wide bandgap dielectrics? Right? Just a question that you have that you're like, I wonder. And then the time it ended at 8 point. Seriously, you're not going to let me write anymore? 8:41 or 8:41 a.m. So that's how you're reporting on your talks. Yes, ma'am.
So we have to ask a question.
No, you have to think of a question.
Oh.
If you ask it, that's great. You don't have to ask.
But we have to write down a question.
Yeah.
Okay.
So you have 4 of those. So 3 on this page, another one at the top of this page, and then I put a dark banner to separate. Then the posters. The poster sessions are all in Ackley Hall. So I put Ackley here, and then you put which one you went into. So let's say I did 109. And, check out both rooms. The time you went there, the title of the poster, the authors listed on the poster, and then the specific person you spoke with. And you can, you can just circle one of the authors and, just go, that one there. That's fine, right? You don't need to write James White twice. Sometimes the person that's presenting is not on the poster, which is rare but and odd. And then this one, you need to interact with the person and ask them a question and write down the question you asked them and the answer they gave you. And of course, it doesn't have to be verbatim. I'm not going to know what's verbatim, but of it. So you have 2 posters that you have to do. Then remember, turn in. So we'll just do it on paper. We're not going to submit them on Moodle. Turn in your name badge along with your paper here with the 6 summaries. And they'll be due at class time on Monday. Any questions about that? Okay, DJ first.
Just a brief overview. How is this going to be kind of graded? So I don't like how much to actually put on.
I am going to grade it by making sure that you filled out every piece and that it's accurate as much as I can tell. And, I will be at the talks I'm at, I'll be taking an inventory of who's there just to make sure we don't have. I have once caught a person who said they were at a meeting that I was in and they weren't there. Of course, I assume everyone's going to be honest, but I got to do my due diligence. So it's not like I'm looking for something major, just completing it and being accurate and showing thought, right? With your notes, you don't want it to be, his hair was a different color than I thought. That would be ridiculous. Lydia.
You said that this could be completed in how much time?
If
we get there, let's say if we go right at 8, what is the?
If you go at 8, you could easily be done by 9:30. Because if you're there at 8, you can get your 4 talks before the break, and then the posters are during the break. And once the break's over, you'll be done. Other questions about this? Now you see that Lisa is here for class again. Thank you, Lisa. And that reminds me that I gave you that, reflections on Moodle to please complete it by tonight. And she knows who's answered, who's been naughty or nice. I don't know, but she will give me a summary without any names attached. And it counts as a homework instead of us having a regular homework tonight. So make sure you do that.
Oh, okay, so it's tonight. We have to have it done by
Yeah. Check.
Where's it located on Moodle? So I looked last night.
I think it's at the top.
Yeah, it's a very
Yeah, it's at the top, but I will just show you rather than. Come on, Moodle. Okay, so right here at the top, we have physics course reflections. You can't see the teacher evaluation yet. That will be coming in a week or so. And I haven't put it up, but I will also put this handout, a link here right below the course reflections, as well as the link to the program that has all of the talks. So you can look through and plan. Lydia.
I kind of remember my question I was going to ask you previously. So for Friday, we have this NAS thing.
Yes.
Do we still have expert TA homework then due Monday too as well?
No. Your homework on Monday will be this report. Yeah.
So this might be a really bad question, but technically this could be one of our draft homeworks, correct?
No.
Okay.
No, this is not one that can be dropped of the homeworks. It is good to ask that rather than assuming and like, wait, if I had known, I would have. Yeah. All right. Let us then get into physics. So we have been talking about, and yes, got the right one. We've been talking about quantum mechanics. And I'm going to do just a little bit more on quantum mechanics, and then we'll talk about theories of the atom. So with quantum mechanics, the wave function is important to us. It gives us the information about, well, the first thing is it gives us the information about where we're likely to find the particle. Remember, we made the analogy between the electric field and the amplitude of the electric field tells us the likelihood of finding the photon if we measure. And the wave function, which is the matter wave equivalent to electric field, that if we take the square of the amplitude of the wave function, it tells us about the probability of finding a particle like an electron. But then when we apply boundary conditions, if we have a particle that's bound in a certain region, it's also going to restrict so we can only have certain energies. So a confined particle has quantized energies. That's where the word quantum comes from. If the particle is confined, it can only have certain energies. And even more interesting, those energies aren't going to be zero. Now, that seems odd because if I take this and I set it down and I say my potential energy is defined as zero where it's sitting, what's its total energy? And we're not using relativity, we're not using rest energy as mc squared. What would you say for its total energy here? If its potential energy is zero, what's its kinetic energy right now? Zero, so its total energy is zero. But quantum mechanics says nay. Quantum mechanics says this is confined to be within this room. It can't get out of the room. And because it's confined to be in this room, it can't be at rest. That makes about as much sense as all the relativity stuff we learned, right? But that's what quantum mechanics says. That brings up an interesting thing when we talk about temperature. What is absolute zero?
When everything is stopped.
No.
We say when everything is stopped, but quantum mechanics says it's not possible for everything to stop its motion. It's still going to have some kinetic energy. So it becomes everything's in its lowest possible energy state, even though it's not completely at rest. Which, that's why some people will quibble when they say, oh, absolute zero is when everything ceases motion. Technically, no, because that's not possible. So we use this Greek letter psi. Greek letter psi as our wave function that does the same job as the electric field did for a photon. And we're going to look very, very briefly, we're talking 10 minutes briefly, at the particle in the box problem. And so this is going to be Chad's third time going through it now. He's just the happy one. a particle in a box, the idea is that I have a potential energy function, which I'm sure is on the next slide, that is potential energy approaches infinity everywhere outside of this region. And we'll have, because the reference point is arbitrary, potential energy is 0 inside. So if you think about that, if I put this in a box with infinite walls, it's got to stay inside the box. It can never get out. It's never going to have enough energy to go over an infinite barrier. So that's why we call it a particle in the box. It can't get out of the well. And then if we start with that, we're going to say, now what does that tell us about the particle? And you can start off with some simple things like, well, I know its position is going to be somewhere between this side of the wall and that side, or this side of the box and that side of the box. Right? So you have some position information right from the start without doing any quantum physics calculation. But we're going to take an analogy to what we had with a wave on a string. If I had a wave on a string, instead of having this box, I thought I had a picture there and I didn't. If I had a wave on a string, I would have a certain condition at each end of the string. What's the condition at each end of the string? Like guitar string. What was the condition at each end? Connected to something it can't move, right? So its displacement is 0. Its amplitude, amplitude, displacement, amplitude is maximum displacement, has to be 0 at the edges. Well, we have the same thing here because you can't have the particle outside of the box. And so it's going to have 0 for its displacement or its amplitude at each end. And then it's going to set up standing waves just like a wave did on a string. So there's a standing wave where it can go anywhere between those. So it can be moving like this. Remember us going over this with waves on a string? All right. We could also have it, it's got to be fixed on the ends, but it could be going like this. Could have a standing wave like that. As long as it has a node at each end, it's good. And so we worked out before that gives us the relationship that the length of the box is equal to an integer multiple of 1/2 wavelength. Right, so it could be 1/2 wavelength, that's this bottom one. Length equals 1/2 wavelength. Here its length is equal to 1 wavelength, or let's put 2/2 wavelengths. If we did the next one, length would be 3/2 wavelengths, and so on. So the length is an integer multiple of a wavelength. Now our box has the length fixed. So the length is not changing, it's wavelength that must be changing. So we solve this for wavelength to say that wavelength equals 2L/n, and we put a subscript n with that wavelength because we have different wavelengths that could resonate on a string. Or for our matter wave, because we're using the same physics really, now just talking about a particle in a box and saying there's a matter wave to describe it. And so that's this equation right here. And if we want to use the de Broglie wavelength equation, since momentum is, well, de Broglie wavelength, remember, was wavelength is equal to Planck's constant divided by momentum. Then momentum is Planck's constant divided by wavelength. And so this is the equation for momentum. So we only have certain wavelengths and only certain momenta that are allowed according to what we've done right here. There is a problem in the analogy I have to bring out right here. We learned about Heisenberg's uncertainty principle in class Monday. And Heisenberg's uncertainty principle says I cannot know the position and the momentum identical, at the same time. There's a certain uncertainty between that product. And so this momentum, either I'm going to know the momentum exactly and not know the position exactly, or vice versa. I can't know them both exactly. Or I can be fuzzy on each. And in truth, with this solution, we know the momentum and not the position. So here's pictures that correspond to the particle in box solutions that I just drew. And if we go through and do our calculations, since kinetic energy is momentum squared over 2m, remember kinetic energy 1/2 mv squared, but since momentum is mv, v squared can be written as momentum squared over m. And so that's how we get kinetic energy is momentum squared over 2m. And since momentum, by the way, notice here potential energy, I use the symbol U for it. These are graphics rather than equations that I wrote. That's why it has the U in there. But using our potential energy 0 inside the box and kinetic energy is p squared over 2m, then we actually calculate that the energies available for the particle in the box are Planck's constant h squared over 8 times the mass times the length of the box squared times n squared, where n is an integer, 1, 2, 3, 4, 5. So we only have certain energies that the particle can have. And it cannot be n equals 0. It has to be n equals 1 or bigger. So that's what quantum physics is really about. We have now found there's only certain energies that particle in the box can have. And Chad probably right now is like, why didn't we do it this way in quantum class? Because I was building to a higher understanding that you don't get to this formalism. So the energies, I can write E sub n is equal to E1 n squared, where E1 is this thing here, and I can calculate all the different energies. And notice that's n squared. They're not equal steps. I'm going to have E1, 4E1, 9E1, and so on, because of the n squared. So what we have here is quantization. Because we have restrictions on its space, it gave us only specific energies that were available. Now we're going to take that and we are going to, I'm going to skip over this. We are going to apply it to an atom. And so I'm sorry, Lisa, mostly today it's a history class. Talking about the history of our understanding of an atom. So if we go back to the late 19th century, which means the late 1800s, we had Thomson, who was studying cathode rays. That is, they discovered that if you have, notice the negative is the cathode. I've never figured that out because cathode is positive as far as I know. The negative is the cathode here. You have the anode here, which is positive. Once again, I don't know why the names have been changed. That you have something that travels through here. They saw that when it hits the end, it made a glow. And so scientists like Thomson were really excited because, you find something interesting. If you're a scientist, you find something interesting, you hypothesize what's making it, and then you test your hypothesis so you can learn and build up a vast knowledge about it. We hope it's vast. So in studying this, Thomson discovered that it responded to magnetic fields, and it responded to electric fields. What kind of particles will respond to both a magnetic field and an electric field?
Electrons.
Okay? More generally, any particle that has an electric charge that's not zero. So it couldn't just be light because light doesn't have an electric charge. It had to be something else. And so by measuring, putting an electric field, putting a magnetic field, they're perpendicular to each other, so one's going to make a force up and one makes a force down. He was able to calculate the charge to mass ratio. And then Millikan, I don't know. Yeah, I don't have Millikan's experiment here, but we have the charge to mass ratio was determined by Thomson. And then Millikan, I do have Millikan here. He devised an experiment where you have little droplets of oil, and, I'm sorry, and by measuring the rate at which the oil moved up and down when there was no electric field and when there was, he found that there were only specific charges that were on the oil drops. And so he was able to analyze and say, okay, charge comes in 1 times this, or 2 times this, or 3 times this. So the charge was quantized. And so the thing carrying the charge, going all the way back to Benjamin Franklin, was determined to be the electron, and the thing that was making the cathode rays was determined to be the same thing, the electron. And so combining these two relationships, Thomson was able to calculate the charge to mass ratio. And Millikan was able to calculate the amount of charge because you have 1 times this or 2 times this. And so if you have the charge and charge to mass ratio, then you're able to get the mass. And so putting these together, we now have, okay, here's an electron, here's mass, and matter, things like this test, has electrons in it. Well, at the very least, metals, because in Thomson's experiment, he was using a metal cathode. And so Thomson said that it must be that the nature of matter is that you have, oh, this is pictures from Millikan's experiment. I didn't realize I had those in there. It must be that you have a slurry of charge. So this is all positive stuff, just spread out nice and smooth like butter. And then you have these electrons, these little points of negative charge. And so this was called the plum pudding model. I think of it as the oatmeal with raisins model. Plum pudding's not something I'm familiar with eating. Oatmeal and raisins, sadly, I'm familiar with that one. And so the oatmeal would be this positive oatmeal / glue, right? Because that's kind of what it tastes like when you're eating it. And then these raisins here are the electrons. So that was the model of the atom that was believed in the very early 1900s. That's not the model that you're used to today, is it? So we've gone forward from that plum pudding model, and the big experiment to break up the plum pudding model was the experiment done in Rutherford's lab. Ernst Rutherford had working for him Geiger, who's actually kind of famous because you guys have heard of Geiger counters, Geiger Mueller counters, if you want to be complete on the name, because it wasn't just Geiger, it was Geiger Mueller. They were studying radioactivity, and they were studying things we call alpha particles, which we know today is helium nuclei, 2 protons and 2 neutrons. And so they're working with these alpha particles, and they have in their lab a newbie researcher, Marsden. And Geiger, as I read the story, goes to Rutherford, says, you know, young Marsden here, he's ready to do his own experiment. Instead of it being like physics lab where I tell you what to do and you do it, we're just going to give him some general parameters and see if he can go do it on his own. And so Rutherford says, sure, I've got something that's been bouncing around in my head. Let's see what happens if we take gold. Gold is malleable. That means you can take it and you can hit it with a mallet, and instead of fracturing, it just squishes. And so you can beat gold to make it very, very thin, what we call gold leaf. And so he said, let's make a really thin sheet of gold. And so they made a really thin sheet of gold, a sheet of gold that's only about 10 atoms thick. Now, they didn't know about the atoms we know today, but using the thickness they were able to achieve, we know it was about 10 atoms thick, very, very thin. And then let's fire these alpha particles at it. So according to the plum pudding model, you mash that so it's only about 10 atoms thick. What you have is this layer here that's mostly going to be empty with maybe a little electron here and a little electron here. And then you shoot these alpha particles at it. The alpha particle has a mass that's enormous compared to the mass of the electron. So if the alpha particle has a charge of +2, if it comes and hits this stuff, it's hitting this positive charge stuff. It's going to be repelled a little when it comes in. It's going to be repelled a little when it leaves to get back its speed. It might lose just a little bit because of the interaction, but it should just basically go right through. Now, if it hits the electron, you know, the alpha is like a bowling ball, and the electron is like a gnat. What happens to the bowling ball when it hits the gnat?
It gets dirty.
It gets dirty. What happens to its energy, to its speed? Nothing really. So it comes out, it will lose just a very small amount And so Marsden was going to measure carefully as carefully as he could. Okay, so how much energy does it lose? So Marsden does his experiment. And what he finds is most alphas came through with no change whatsoever. They just went through like they hit nothing. But every now and then you'd have an alpha particle that would come careening out at basically the same speed it came in as. And some of them would come straight back at you. So they were going at crazy angles, not a lot of them, but some of them. And that could never happen. You're never going to have a bowling ball hit a gnat and come bouncing back at you, right? So when Rutherford was on the circuit talking about his great scientific discovery, who made the discovery? Marsden. But it was in Rutherford's lab, hence Rutherford is the one that, it's always called Rutherford gold foil experiment. So he's on the circuit and he's like, well, this is the way we thought it would be. It's like we put up a roll of tissue paper, or no, a sheet of tissue paper, and we fired a cannonball at it. And then it bounced back at us. That's how shocked we were. Well, what does this tell you that it bounced straight back?
There must be something of significant mass.
There must be something of significant mass. This must be like we're shooting a BB at a bulldozer. Because it's just bouncing back, not even losing any energy, so it's, very much. And so now Rutherford did a lot of work on this. He didn't just say, okay, we're done. Right? If you're a scientist, you found something really interesting. So you hypothesize, as DJ said, there must be something big and massive there. And so they studied it more carefully, determined it had a positive charge, and he was able actually to determine the radius of it. And so he said, we have the model all wrong. We have most of the mass that's in matter is in a really small volume. And then it must be mostly empty space if most of the mass is in a small volume, with the electrons orbiting that empty space. So he said it's like a planetary system. It's like a planetary system. Okay, so this is showing pictures of the experiment. I don't want to go there yet. It's like a planetary system where you have the nucleus here, which has a positive charge, and then you have electrons that are like planets that orbit the nucleus. And even though at that point they knew that planets didn't do circular orbits, he said that we have the planets, the electrons, are doing circular orbits around the nucleus. So it's a new model. It makes sense in light of his experiment. And I hate to admit it, but when I came to college, and even while I was taking physics class, I thought this was the model we believe. Right? You've all heard of this model, but it wasn't right. And in fact, they figured out immediately it wasn't right. Why is it not right? Well, there's some few basic things that really tell you it's wrong. So reason number one that it's wrong, electromagnetic theory, which was well worked out at that time, says if you have a charged particle and it's accelerating, and of course if something's going in a circle, it's changing direction, so it's accelerating, then it must be giving off radiation. Remember we talked about X-rays. What's producing the X-rays? The thing we call bremsstrahlung. Any German speakers?
Oh, I was just about to say that.
Ich spreche keinen Deutsch. It's called bremsstrahlung. It stands for, it means in German, breaking radiation. Because the electrons were slowing down, they were giving off radiation. Anytime you have acceleration, it gives off radiation. Which means energy is going out. So if I had an electron that was doing a circle, it'd be constantly giving off radiation, and energy would be dropping, which means it would slow down and spiral in and crash in the nucleus in like a nanosecond. So any atoms that we had would be gone in a nanosecond. Couldn't be the right model, could. There's some other evidence to suggest that this was not right. And we'll go through that other evidence just after I ask you this question. what did Rutherford expect would happen when Marsden fired alpha particles at a thin gold foil? Just to make sure you followed the story. What was his expectation? C. Most alphas would be unaffected. That's right. He thought they'd just go through unaffected. Maybe slow down a very small amount. On tests, I would try not to have two answers that are so close. Not going to be absorbed, not bounce at random angles. Those were not expectations. Okay, so here's a picture of his model. Remember, I told you he actually was able to determine the size of the nucleus, about 10 to the minus 15th meters.
Speaking of the test, are we going to have, since we're not going to class on Friday, are we going to have the review sheets by the weekend? Are we going to have this time?
I have forgotten about that. I will do them, yes.
Thank you.
Yes, because all we're going to have between now and the test is a review on Monday, right? Yeah. So, yes, I will do that. Thank you for reminding me. Pretty off topic, but important.
We had just mentioned the test and wait.
Yes.
Is that going to be, is this going to be in the test?
Yes, this will be on the test.
Okay.
So, another thing that was evidence for the failure of Rutherford's planetary model. Remember when I brought out the lamps and we had the cool glasses so that we saw the colors and only specific colors? Well, that means that we had quantized energies for the electrons in the atoms. That the electrons must have been going from one energy state to another discrete energy state. And the light that we're getting is the energy difference between those states. But this planetary model, planets don't have to orbit at certain energies or certain radii from the sun, right? They can be at any distance from the sun. And so that's another, it wasn't quantized like we know we must have for the electrons in an atom. So Danish physicist Niels Bohr, this pictures of what we saw with the glasses, except for this is looking at more than one gas, right? I think only looked at one gas. You have different spectra for each different element, which tells us that the electrons must have different energy levels for different elements. So you don't take the hydrogen energy levels and apply them to helium. It's not going to work. They're going to be different. Experimentally, I think he was like a high school teacher, Balmer said that we can actually make an equation to give us the wavelengths that we see in the emission from hydrogen. And that equation is 1 over wavelength is equal to R, which just is the Rydberg constant. It's a constant number, which I wrote down there at the bottom, times 1 over 2 squared minus 1 over n squared, where n is any integer bigger than 2. Basically, he was intelligent. He saw a pattern, a kind of convoluted pattern. This isn't the kind of pattern that I'm likely to have picked out. But he saw a mathematical pattern. And then something I find really funny. This produces visible wavelengths. Well, as technology improved, scientists were able to measure infrared as well as ultraviolet. And so Lyman said, hey, this ultraviolet light, I can come up with my own equation to describe the wavelengths of the ultraviolet light. I'm just as good as Balmer. And my equation is 1 over wavelength is equal to the Rydberg constant times 1 over 1 squared minus 1 over n squared, where n is any integer bigger than 1. That's a big shift, isn't it? And then in the infrared range, so that was Lyman, Balmer, somebody then bracketed food. Uh-oh. I forgot the next person. Said, hey, I can come up with an equation for infrared that's just like this, except for this is a 3, and this is any integer bigger than 3. Then I think Brack is, hey, I can come up with one that this is 4, and this is any integer bigger than 4. Obviously, there was a pattern here. There was no scientific reason for this pattern. It was observed. And so here we have Paschen. That's it. Paschen was the one with 3. So we have the Lyman series, the Paschen series, the Brackett series, the Funtz series. And so here we see the wavelength. So this is a spectrum showing the ultraviolet, visible, and infrared. And you just have those different sequences of emission lines. So once again, these can't be explained by Rutherford's theory. According to Rutherford's theory, it should just be continuous spectrum. So enter Niels Bohr. Niels Bohr says, let's just make some assumptions. We're going to start with some beliefs here. So assumption number 1, electrons orbit the nucleus in circular orbits. Okay, that's the same as Rutherford, circular orbits. And by the way, just jumping to the end, that's not what we believe anymore. And these stationary orbits, as he called them, have discrete energies. So you have this energy or this energy, and you can't be anywhere in between. That's the idea of quantization. So you had quantized energies, which had to exist because of what we observe with the emission spectrum. But then he makes an addition on this that says they can't follow classical physics. They don't radiate as they orbit because that would require a continuous change in energy. But it can't have a change in energy, so it's not allowed to radiate. This still sticks in my craw. That just doesn't make sense to me to say, well, we're going to have to violate this law because of this law. But that was his second assumption, that they have specific energies, and so they can't radiate because they're stuck in one energy and can't change. The only way they can change is to change from this specific one to this specific one. So that's what assumption number 3 is, that they will stay in one energy level unless they jump from one allowed energy, one stationary state, to another stationary state, in which case, if they drop to a lower energy, they're going to give off a particle of light. What's the name for particle of light? Photon. They're going to give off a photon with an energy equal to the gap. So that's how you can get those specific energies in the spectra, because the energy of the photon is equal to the energy of the gap. Or if it absorbs energy, it could go from the lower one, so it could go from EL to EU, if it absorbs a photon with exactly that energy. Now remember, the energy equation for a photon is HF. And so what you have here is the starting energy minus the ending energy is equal to the energy of that photon they gave off. And then we finally have his fourth assumption, which is that the angular momentum must be quantized. As I understand it, this wasn't the first idea he had for quantization. It was the last one. It was the one that turned out right, where he didn't have to try another one. And so he said the angular momentum the electron has as it orbits the nucleus. If you're doing a circular orbit, angular momentum is just mass times speed times radius. And so he said the mass times the speed times the radius must be simply an integer multiple of h bar. Now, I don't remember, did we talk about h bar in this class, or was it only in 252?
We talked about it a little bit, I think.
Okay. H bar is the basic unit of angular momentum. It's Planck's constant, the 6.626 times 10 to the minus 34 joules times seconds, divided by 2 pi. So that's the definition of H bar. And we use it so much that that's why we have a new symbol for it. So the angular momentum could be 1 times H bar, or 2 times H bar, or 3 times H bar, etc. So these were the starting points of Niels Bohr. And so then he used classical physics from there. So using classical physics, we have an attractive force between the nucleus and the electron. Force is equal to, remember, we learned the equation. Coulombic force is equal to K Q1 Q2 over R squared. Q1 here is the charge of the nucleus. So Z is an important symbol. Z is the number of protons in the nucleus. So the charge of the nucleus is the number of protons times E, which is the size of the charge of the proton. And then, of course, we have orbiting the electron. So Q2 is that charge of an electron. Now, if I have something going in a circle, I know acceleration has to be v squared over r if it's going in a circle. And I know Newton's second law. Sum of the forces toward the center is mass times acceleration toward the center. And so combining the equation, the equation in black, the one inside the magenta box are the same. Combining this equation with this equation into this equation, he was able to solve to find the radius at which the electron is orbiting. And from that radius, he was able to then use the equation for his quantized angular momentum to find the speed it was orbiting with. And from those two, he was able to find the energy it had. And so Bohr's model gave him a radius that was equal to this stuff here, n squared times the Bohr radius. Here's the Bohr radius. It says equals R1 on the other side, but just putting it closer. So it's n squared times the Bohr radius divided by z, the number of protons in the nucleus. And based on that, like I said, he was then able to calculate the energies. And I don't have the energy equation written here. I'm also totally out of time. Well, he was able to calculate the energies. Energy sub n is equal to E1, and I'm going to not worry about the z's here, times n squared, where E1 for hydrogen atom is minus 13.6 electron volts. Not times n squared, over n squared. So he's able to come up with specific energies. And then going back to that equation from, assumption 3, that said the energy difference was equal to the energy of the photon. We have HF is equal to E1 over n initial squared minus E1 over n final squared. And it gives us the same equation since F is equal to C over lambda. So his work reproduced gave us a physics reason for the laws of Balmer, Lyman, Pasch, and Brackett-Fund. Great start, not correct. That's where we will end for the test.